So this is another type of multiple trials that we might see. So again, it's asking for multiple selected people, multiple selected objects, individuals, whatever, right? And this time it's going to say exactly a certain number of outcomes. So we'll see a little bit, especially in our example number 1, but this is what happens. So if you're trying to find exactly some number of outcomes, so it could be, exactly 1 outcome, exactly 2 outcomes, exactly 3 outcomes, so on and so forth, right? So what you want to do is you want to list out all of the outcomes. With the requested objective. So if it's exactly 1 outcome, you need to list out all the ways that that 1 outcome can occur. It probably will be more than 1, and by probably it will be more than 1. Same with 2, same with 3. And we'll see, like I said, it'll all make sense hopefully when we start doing some examples. So then you want to find the probability of each of these outcomes. There will be, like I said, more than 1. Using the strategy for multiple trials. So we had an earlier video talking about multiple trials. That's what we're going to be using. Then what we want to do is add all those up. So another strategy that we could do if you're trying to get some number of outcomes, find the probability of 1 outcome and then multiply that number by the number of outcomes. Because you'll end up seeing that all of the outcomes have the exact same probability. So instead of adding them all together, you can just multiply it by the number of outcomes. All right, so that's a lot of words. Let's actually see what this looks like. Example number 1, suppose that you flip a fair coin 3 times. Find the probability that you get heads exactly once. All right, so this is exactly 1 outcome, right? Exactly 1 time. So the way we do that is how many ways for 3 coins can you get exactly 1 heads? Well, you could have heads first, you could have heads second, and you could have heads third. Right? So there are actually 3 outcomes for the 3 different times. So what's the probability of getting a heads? So let's find, so we listed all the outcomes. Let's talk about probabilities of each outcome. So the probability of getting a heads is 1/2 times probability of getting tails is 1/2 times probability of getting tails is 1/2, right? These are all independent, so they don't affect each other. So when you multiply all these together, you get 0.125. So let's do the next one. Probability of getting tails, 1/2. Probability of getting of heads, 1/2. Probability of getting tails, 1/2. This is the exact same thing, so it's 0.125. And again, you can see, right? This is going to have the exact same probability. 1/2 times 1/2 times 1/2, which will be 0.125. So if we add all these up, we end up with 0.375. So the strategy that we talked about was that, funny enough, these probabilities will always be the same for this class. So another thing that you could do is once you find one probability, you can just multiply by the number of outcomes that you found. So we had 3 different ways that you could get exactly 1 heads. So we just multiply it by 3. And you see that we end up with the exact same answer. Now again, this might be a little hard for some people to see, so let's just do it the other way, right? So if we actually listed out all the different ways that you could get 3 coins, 3 coin flips, remember we had heads, 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 tails, tails, tails. We could have 1 heads and 2 tails where heads is first, heads is second, heads is third. Or we could have it the other way, right? Where you have, oh, we should probably have the third one. There we go. Or you can have 2 heads and 1 tails, where tails is first, second, or third. So we can see that out of here, right, we have exactly 1 heads 3 different times out of a total of 8, which is 0.375. So again, you could do it this way, but if I asked you for 15 coin flips, right, that's just going to be a lot more work than doing it this way. But this is kind of how we're getting this. Let's do another one. So example 2 in roulette. So we've talked about roulette before. We have slots 0, 00, and 1 through 36. So if someone plays the game 4 times, what's the probability that the ball will land in the slot number 17 exactly 3 times? All right. So first thing we got to do is list out all the different ways that you can have 17 exactly 3 times out of 4. Well, the first time it could be 17, 17, 17, and then something else. Now, it doesn't matter what that something else is, right? It could be 0, 00, it could be any other number. So really, it just matters that it's not 17. We could do another one, right? Where the one that's not 17 is last. We could do not 17 is third. Not 17 is second. And the not 17 is first. All right, so there are 4 different ways of doing it, which kind of goes along with our 4 different times. All right, so what's the probability of getting a 17? So remember, there's one way to get a 17 out of 38. 1 through 36 is 36 different ways, 37, 38. And 17 is one of them. Times, again, these are independent, so 1 out of 38 times 1 out of 38. And then how many ways can you get not a 17? Well, 17 is one of them. Then we would see that there are 37 other ways of getting something other than a 17, right? And again, if you notice, this will be the same probabilities for all of them, right? This will be 1 out of 38, 1 out of 38, 37 out of 38, and 1 out of 38. And so really we're just multiplying them in different orders, but they're the exact same numbers, right? So when we multiply these out, we get, when you move the decimal, 0.0000177 about, right? Now since we have 4 different outcomes, we can just multiply this number by 4, and we get that our final answer is 0.00007. And that's it. Number 3. So a bag contains 4 blue M&Ms, 6 yellow M&Ms, 3 green M&Ms. Find the probability of randomly picking and eating exactly 1 green M&M if 4 is eaten. All right. So 1 green M&M out of 4. So the green M&M could be first, and then it would either be blue or yellow for the next ones, right? So it doesn't matter which one they are. We can just put X's. It's not green. This is the important thing. Green can be second. Green can be third. Green can be last. So looking at the first one, what's the probability of getting a green? So there's 3 green out of a total of 13. All right. So we have eaten this green M&M. So we go down. We have 1 less M&M total. Now, how many different M&Ms do we have that are not green? Well, this isn't going to go down because remember, if we ate a green M&M, then we still have 3 blue and 6 yellow. So we still have 10 M&Ms that are not green. Now, if we eat that one, right, if we eat a blue or yellow M&M, that means we have, again, 1 less M&M and 1 less M&M that's not green, right, because we ate either a blue or a yellow M&M. And likewise, if you eat another one, right, 1 less M&M, 1 less one that's not green. When we multiply all these together, we end up with 0.12587, blah, 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 right, about that number. And you can see that this is actually going to be the same, right? So just to clarify, if we have the first one is not green, well, there's 10 different ones at the start out of 13. We ate one, so there's one less green M&M. Or sorry, there's one less M&M. But since we only ate from the blue or green, we still, or sorry, blue or yellow, we still have 3 green M&Ms, right? So if we eat a green M&M, we have one less M&M. And remember, since we've already eaten one M&M that's blue or yellow, we have one less M&M. So now we just have 9 non-green M&Ms. If we eat that one, right, then we have 8 non-green M&Ms. And again, if you notice, these are all the same numbers on the top and the bottom. So when you multiply this out, you get the exact same number. And you can see this works for all of them, right? So first one, we have 10 over 13. If we eat another non-green M&M, that's going to be 12 out of 9. If we try to get a green M&M, we haven't eaten any green M&Ms, so that's still 3. And then if we have another non-green M&M, well, we already ate 2 of them, right? So we have 2 less. And again, same number. And likewise, this will be the same number. So we can either add those up, or you can just do this one time, multiply it by the 4 outcomes that we have, and get about 0.503. And that's our final answer. All right, last problem for this section. So Tire Factory selects a sample of items without replacement. They will accept an entire batch if exactly one time in the sample is defective. Sorry, that should say tire. Exactly one tire in the sample is defective. All right. So in one day, a factory manufactured 2134 tires, and 468 of them were good. So if 5 tires were randomly selected for testing, what's the probability that the entire batch will be accepted? So again, the entire batch is accepted. What does that mean? Let's go back to our problem. We will accept the entire batch if exactly one tire is defective. And we have 1 defective out of 5. So let's look. Same thing with all the other ones, right? Let's list out all the outcomes. The first one could be defective, and the other 4 are good. The second one could be defective. The third one could be defective. The fourth one could be defective. Or the last one could be defective. Now we gotta ask ourselves, what's the probability that the first one is defective? Well, notice that if there are 468 good out of 2134, then if we subtract these numbers, right, we'll get the number of defective ones. So the probability that the first one's defective is 1,666 divided by the total. All right, so notice this is without replacement. So we have not replaced that defective tire, so we have 1 less tire. So from here, how many good tires do we have? Well, we haven't taken a good tire out, right? So we still should have 648. Again, if we took out a good tire, we have 1 less tire. And since we already took out 1 good tire, we will have 1 less good tire. All right, and we can just keep going down, right? We have another less good tire, and another less good tire. So when you multiply all this together, you see that you get, after using scientific notation, about 0.0000385. Since there are 5 outcomes, we just need to multiply that by 5. So our final answer is about 0.00002. So 4 zeros after the decimal. All right. Hope that helped. If you have any questions, like always, feel free to contact me. Have a great day.